Ever wondered how AI learns to follow directions like a human? Not just memorizing patterns, but understanding what it's looking for. That's the heart of semantic navigation, a field pushing AI to interpret language and translate it into physical actions. Today we're diving into a breakthrough called MLFM, a method that's redefining how machines see and understand their environments. Let's break it down. Imagine an AI agent dropped into a virtual room, tasked with finding a small blue book on the shelf. Sounds simple, right? But here's the catch. The environment is cluttered with hundreds of objects, and the AI must parse language to narrow down the search. Traditional systems rely on basic 2D maps that lack critical details like color, size, or spatial relationships. It's like trying to find a needle in a haystack with a blurry photo. Enter LangNavBench, a dataset designed to train AI on precise, human-verified instructions. Unlike AI-generated prompts, these commands are meticulously crafted. A small blue hardcover book on the top shelf. This precision reduces ambiguity, giving AI a clearer roadmap. It's not just about following directions. It's about building a shared understanding between humans and machines. Now here's where MLFM shines. This approach uses a multi-layered map to represent environments. Think of it as a 3D puzzle. One layer for floor-level objects, another for mid-height shelves, and a third for overhead structures. This layered architecture lets AI distinguish between a book on a table versus one on the floor, without the computational burden of full 3D modeling. It's like giving the AI a multi-tiered mental map, prioritizing relevant details in real time. The numbers tell the story. MLFM boosted task success rates by 30% compared to older methods, while improving path efficiency, SPL, by 11.5%. Why? Because the layered map focuses the AI on critical features. If the goal is a candle on the TV stand, the system prioritizes the stand's surface, ignoring irrelevant areas. It's like a GPS that highlights only the route to your destination, not the entire city. But MLFM isn't flawless. It struggles with subtle distinctions, like differentiating silk from cotton or abstract phrases such as the door that's open. These gaps highlight the need for future work, refining perception systems to handle texture, context, and dynamic environments. Why does this matter? As AI steps into real-world roles, like guiding delivery drones or assisting in households, its ability to interpret nuanced language becomes critical. LangNavBench and MLFM aren't just incremental updates. They're foundational steps toward creating systems that understand the world, not just react to it. But here's where it gets even wilder. Researchers also explored how AI balances exploration and exploitation, the classic trade-off between learning new info and using existing knowledge. Their experiments revealed a sweet spot, 40% exploration time, followed by 60% exploitation. Too much exploration and the AI runs out of time, too little and it misses key details. It's like a student who either overstudies or cramming, neither works. Balance is everything. They also tested the role of environmental maps versus object detection. Surprisingly, the map alone performed nearly as well as the full system. But remove it entirely, and performance plummets. It's like driving without GPS. Your eyes can spot traffic, but without a sense of direction, you're lost. The map isn't just a tool, it's the backbone of smart navigation. Then there's text-as-a-kernel, a method where AI uses language to query its map. For example, if told, "Find the black leather couch," the robot doesn't scan randomly. Instead, it leverages its map to pinpoint the couch's location. This approach bridges abstract language and physical objects, enabling AI to tackle complex tasks with minimal training. It's like giving the robot a dictionary and a compass. Now it can follow directions, not just react to stimuli. Finally, they tested MLFM on GoatBench, a real-world dataset. The results? MLFM outperformed cutting-edge methods, even in zero-shot scenarios, meaning the AI didn't need explicit training for every task. It learned to navigate by understanding language and building adaptive maps. It's like teaching a dog to fetch by describing the ball's color and location. No trial and error needed. So what's the takeaway? Small changes, like optimizing map resolution, balancing exploration with action, or using text to guide decisions, can revolutionize AI navigation. It's not just about coding smarter. It's about equipping robots with tools to see, remember, and understand their world. Thanks for watching. If you want to dive deeper into these ideas, hit subscribe. Until next time, keep exploring.